We're going to talk about in this video some of the problems from section 4.6 that deal with particular functions that arise a lot in discrete mathematical problems. The most important ones are what are called the floor function and the ceiling function, because these functions allow us to take numbers that are any real numbers and return just whole numbers, integers. And we've seen that a lot of discrete problems are really problems about things that can be described in terms of whole numbers or things whose answer are in terms of whole numbers. So floor and ceiling give us a way of converting non-whole numbers into whole numbers. Maybe surprisingly, the idea of rounding off to the nearest integer is not nearly as prevalent in discrete math applications as you might be used to using it in other kinds of math. So the idea of the floor and the ceiling is very simple. It's just like rounding off a number, except rather than rounding to the nearest whole number, you're always rounding either down or up, depending on which of the functions you're using. And so it's hard to really call it rounding at all, because you're not just trying to get the number to be close to you're not trying to get an integer that's close to the real number you start with. You're trying to get an integer that is related in a consistent way with the real number that you're inputting. So in the notation, we use this symbol for the floor function. Notice it's got the little brackets on the bottom on the floor of the brackets, and we use the opposite of that for the ceiling function. We put little brackets around it, but we only included the ceiling part of the bracket. And so these functions are either going down or going up, depending on whether it's floor or ceiling. It's pretty easy to remember. So for example, the floor of 1.99 is just 1, because 1 is the whole number below 1.99. When you put a whole number in, like the floor of 21, the floor and ceiling functions, neither one of them do anything to whole numbers. The idea is to return a whole number, and so if the input is a whole number, the output is just that same whole number. So so for these other ones, the floor of 3.7 is 3, because 3 is the first number you get when you're going down, the first whole number you get going down from 3.7. The ceiling of 4 thirds is like 1.333 and so on. So going up to the next whole number above that will be going up to 2. Negative numbers require a little bit of thought, because the number is just going up or down, meaning to the bigger number or the smaller number. So keep in mind that if we have negative 12.5, the ceiling of that means the next number above it, the first whole number I come to above that. Above means greater than. And so negative 12 is greater than negative 12.5. Similarly, for the floor, notice that negative 2 is the first number that's less than negative 1.3, and so the floor of negative 1.3 is negative 2. So make sure when you're doing floor and ceiling that you're going to the next number, the next higher number, or the next lower number, and when the numbers are negative, that might be a little bit counterintuitive, but just draw yourself a number line if you're not sure. On a number line, negative 1.3, negative 2 are in this order. So the ceiling means you're going smaller. So the ceiling of negative 1.3 is negative 2. I'm sorry, the floor of negative 1.3 is negative 2. Okay, so how are these applied? Well, we've seen one application before with problems about divisibility when we were talking about inclusion and exclusion. The numbers that are in this set that are divisible by 6, that's 6 times 1, 6 times 2, 6 times 3, and so on. And the question is, how far can you go? What is the highest that you can go and still be in this set? And so what you're trying to solve is, how close can you get? Well, I shouldn't write it that way. How close can you get to 2003 just counting up by 6s? So the way we can figure that out is we can take 2003 divided by 6, which I should have somewhere. Hang on. Yeah, so this is 333.8, more or less. And so what that tells us is that that if we write 6 times 1, 6 times 2, up to 6 times 333, that all of those numbers will be inside of this set. But if I do 6 times 334, it won't be. So this is a good example of why the 4 is relevant, because when you're talking about the multiples of 6 being in there or not being in there, it really doesn't make any difference what this decimal place is. No matter how close you are to the next whole number, that number just is not there. 6 times 334 is not there, regardless of how close this decimal point is to the next whole number up. And so the answer to the question, how many of these multiples there are, is just the 4 of this calculation. So the 4 of 2003 over 6 is 333, and it makes perfect sense that I should be taking the 4 because there's no such thing as a number being 80% in there or whatever it is. You either have a multiple of 6 or you don't, and the decimal place is irrelevant. Number 2 is an example of using inclusion-exclusion as an application of that. So if you have the multiples of 2 over here and the multiples of 3 over here, then the overlap are the multiples of 6. And so, so the answer to this question is, if the first set is A and the second set is B, and the interior is A intersect B, then our answer is just add the size of A and the size of B, but then subtract off the size of the intersection because that would have been counted twice. Each one of these calculations is very quick with this idea that we just established. The number of multiples of 2 is just 2003 over 2, but again, I'm taking the 4. The number of multiples of 3 is 2003 over 3, taking the 4. And the multiples of 6 is the 4 of 2003 over 6. So if I do those 3 calculations and add and subtract, I'll have the answer to that question. Finally, so this is an example where the calculation, that division calculation, takes you outside of the whole numbers. The question has to have it's a whole number question with a whole number answer, but this intermediate step takes you outside of the whole numbers. And so when that happens, we need some kind of function that brings us back into the world of integers, and that's what the floor and ceiling are doing. A more complicated example of this is this next problem. If we wanted to know how many decimal places we would need to display 2 to the 2019, it's kind of a tricky problem because the calculator really doesn't want to do this. If you have a normal like TI 8384 calculator and you ask it what 2 to the 2019 is, it'll just make fun of you. It really can't do it. But we don't need to be able to calculate the number to know how big it's going to be. So the size of a number, the number of digits of a number, is determined by what power of 10 it's near. So let me just show you an example of that. It seems dumb when you're working with powers of 10, but like the reason say 10,145 is a was that a 5-digit number? So I could say because, well, because I can count is really the reason. But what makes it a 5-digit number in our base 10 system is the fact that that number lies between these 2 powers of 5. This is the first 5-digit number, and this is the first 6-digit number. So when you know the number is between these successive powers of 10, then you know that this has to be among the 5-digit numbers because it's not as big as the first 6-digit number. So I can always figure out how big a number is by just figuring out which 2 powers of 10 this number falls in between. And that's actually a much easier question because of something that we have learned in our continuous math world. So what I'm trying to find is I'm trying to find a power trying to find two consecutive powers of 10, 10 to the something and 10 to the one more than that, that 2 to the 2019 lies between. To figure out how to solve an equation like this, I'm going to first solve the inequality like this. I'm going to first solve this equation. What is the power? Let me just take that away. What is the power of 10 that's exactly equal to 2 to the 2019? The way we would do that is by taking the logs of both sides. So the log base 10 of 10 to the x is equal to the log base 10 of 2 to the 2019. This over here is just x. The right-hand side looks no better than it did before. I've just taken a number I didn't want to compute. I did not want to compute this, and now I'm telling it to compute something that I don't even want to think about of something that I don't want to do. But there's a rule of logarithms that allows us to simplify this. When we have the log of an exponential argument, then the exponent can be pulled outside. So log of 2 to the 2019 is the same as 2019 times the log of 2. And that is a very, very easy thing to calculate. So that's 2019 times log 10 of 2 is about 0.30103. And if I do that calculation, I get 607.8. Again, I don't have to round it off very much because I know that I don't want the decimal answer anyway. The question, how many digits does this have, has to have a whole number answer. So what I've determined here is that this enormous number, 2 to the 2019, is in between 10 to the 607 and 10 to the 608. That's what it means to be have the answer to the problem be 607.8. We know it's closer to 10 to the 608, but it doesn't matter because, again, just like before with these 5-digit numbers, we know that a power of 10, I mean how many digits it has, the next power of 10 is the first number with the next number of digits. So we know that this is a 608-digit number, and this is a 609-digit number. And more importantly, this is the first 608-digit number, and this is the first 609-digit number. So since those are the first of their kind, and this is in between, this has got to be a 608-digit number. So again, the operation that I need, because I'm trying to figure out how many digits this thing will take to display, I need to know about what power of 10 it's close to or equivalent to. And so that problem takes us into the world of logarithms, but logarithms do not return whole numbers. Logarithms return real numbers. And so I need to have a way at the end of a problem to take the information that I have in terms of non-decimal numbers and turn it back into a whole number answer. So technically what I've done here is I have taken the log base 10 of the number that I was interested in, and I have taken the floor of it. The floor of it was what told me to go here, and then I'm adding 1. Right. So I looked at the number below because that's this one has the same number of digits. Right. These two numbers have the same number of digits. These two guys. So I take the floor and it tells me what power I have the same number of digits as, and then I have to add 1 because that's how powers of 10 work. Okay, so the number 4 is another problem that that you would do using logarithms, and there's a different logarithm rule that you'll need to simplify that, and I'll leave that for you to do and think about before next week.